So chapter 23 will require us to recall a lot of things that we learned in physics 1, particularly work and energy are going to come up a lot in this chapter. So here is a quick review. So work done by a constant force in moving an object in a straight line by a distance d is given by F dot d, which is Fd cosine theta. You know this from physics 1. And this is if the force is constant and the object is moving in a straight line, then you have this formula, right? The more general formula for work is that it's the line integral of the force in moving the object from point A to point B. So if you have an object that started at point A and ended up at point B, it followed this weird curvy path. And the force also was not constant. It has a different magnitude and direction at every point. Then how do you calculate the work? In general, it's given by this line integral, F dot dl. And what does the line integral mean again? So let me just quickly remind you of that. So we will need the concept of a line integral in this course. You don't need to be an expert at doing line integrals, but the concept of the line integral is very important. So suppose the object moves along this path. So how do we calculate the work? We have our simple formula. Work is equal to Fd cosine theta, or F dot d. That's if the force is constant and the object moves in a straight line. So we had this discussion in physics 1. What you do is you break up the path into these small segments and call each small segment dl. So that's this tiny little segment over here, dl. And so the advantage of taking a very small segment of the path is that if it's very small, you can think of it as more or less straight, right? And also, so that satisfies one of the requirements, it's moving in a straight line. And also the force might be changing from point to point, but over this very tiny segment, it's reasonable to think that the force doesn't change at all, either in magnitude or direction. So there is no problem in calculating the work done over just this tiny segment. And the work done over this tiny segment, we can call that as dw, and that's F dot dl, using the simple formula for work, right? F dot d, because the conditions for that simple formula are met just over this tiny segment. And so the total amount of work done over the whole path is nothing but the integral, or the sum of all of these tiny amounts of work. So that sum becomes an integral, and that's integral F dot dl. And this kind of integral is called a line integral, and you have to evaluate it over the path. So A to B. So you have to evaluate it over the path. In physics 1, I didn't really go over how to do these line integrals. We just went over the concept, and that's also what we need in physics 2. So this is the general definition of work. It's the line integral. That clear to all of you? All right. Now, we also learned that if you have a conservative force, and what is a conservative force? Conservative force means that the work done by the force is independent of the path. So in this example over here, suppose I had chosen a different path to take the particle along. So this is path number 1 and this is path number 2. If the force is conservative, then the work done will be the same, completely independent of the path. So that's a conservative force. And for a non-conservative force, the work done does depend on the path taken. In physics 1, what were the two conservative forces that we saw in physics 1?
Gravity.
Yes, very good. Gravity. And what was the other one?
Spring force.
Yes, exactly. Gravity and the spring force given by Hooke's law. These were the two conservative forces that we saw in physics 1. And I told you that in physics 2, you're going to see one more, and that is the electrostatic force given by Coulomb's law. That is also a conservative force. So these are the only three conservative forces that you're going to see in your study of physics. So we've seen that if a force is conservative, the work done on it can always be expressed in terms of a potential energy. And the connection between work done by a conservative force and the change in potential energy is given by this very important equation. In physics 1, I had a whole slide dedicated just to this equation. WC is equal to minus delta U. So the easiest way to see this is we talked about this in physics 1, but I'll just quickly remind you again. You can see this through the example of gravity. So if I have an object over here, gravitational potential energy is given by mgh. So if I have an object over here and I lift the object up, in that case, the work done by the conservative force, is it positive or negative? So gravity is acting downwards like this. So if I lift the object up, so did gravity do positive or negative work? Did it get its way or not?
Yeah, it's got its way.
No, when the object moved up, then did gravity get its way?
No.
No. So yeah, I'm talking about the object being lifted up. So if the object is, when the object is lifted up, then the displacement was upwards, but the force was downwards, right? And so the work done was FD cosine 180 degrees, which is negative. That makes sense? So I'm talking about the object being lifted up. So the work done is negative. And what happened to the potential energy when the object was lifted up? Did it increase or decrease?
Increased.
Exactly. So the work done was negative, but the delta U is positive. That makes sense? So you can see that there is a relative negative sign between the work done by the conservative force and the change in potential energy. And if the object drops, if you let the object drop from here to here, then it's while it's falling, does gravity do positive or negative work?
Positive.
Yes, Natalie, what did you say?
Positive.
Positive, very good. Because its force is downwards, displacement is downwards. So the work done by the conservative force is positive. And what about the change of potential energy? So did potential energy increase or decrease when it fell?
Decrease.
Decrease, exactly. So delta U is negative. That makes sense? So again, you can see the same thing, that there is a relative negative sign between the work done by the conservative force and the change of potential energy. WC is equal to minus delta U. This formula is actually the definition, the formal definition of potential energy. Okay, so we're going to need this formula here in physics 2 as well. Okay, and then of course, yeah, so we talked about this. The work done by a field, conservative force, results in a loss of potential energy. By means positive work, and work done against a field or negative work results in a gain of potential energy. And of course, there is this equation of conservation of energy, K naught plus U naught plus W other equals K final plus U final. So all this stuff we've seen in physics 1.